Hi, I'm Kyle DeNoble, and this is Lab 4 for Physics 2212. Purpose and fundamental ideas. The purpose of this lab was to predict the behavior of circuits containing resistors in series and in parallel. Fundamental ideas are the loop rule, which is current in equals current out, the equation of change in voltage through a resistor, delta V equals IR, and the equation of change in voltage through a capacitor, delta V equals Q over C. In section 3, the plot of the natural log of V over V naught equals negative t times 1 over RC, shown to the right, had a line of best fit of y equals negative 0.1661 times x minus 0.008. The slope here gives negative 1 over RC, so 1 over RC equals 0.1661. This is to be expected as R times C was 0.2 times 30, and 1 over 0.2 times 30 is 0.16 repeating. The rest of the results will be discussed throughout the experiment portion of this video. Models here. The assumption is that the wire had negligible resistance in the circuit. The system here was the circuit. The models are the images shown to the right. The components of the circuit that are included in the system are the wires, batteries, capacitors, light bulbs, and resistors. Their surroundings are everything else. Observations. When the ammeter was put in backwards on the circuit sim, the value stayed the same as it was when it was put in correctly. When one of the ammeters was replaced by the voltmeter in the circuit, the other ammeter reads 0 amps and the voltmeter reads 3 volts. For the experiment, I will be going through each of the numbered questions on the experiment PDF that will be linked in the description below. For number 1, the predicted currents I1 and I2 with delta V equals IR for the circuit shown in the top right is I1 equals 0.0204 amps and I2 equals 0.0204 amps. The actual currents I1 and I2 measured by the ammeters are the same as the predicted with 0.02 amps and 0.02 amps. For number 3, nothing was different when you put the ammeter in backwards on the circuit sim. For question 4, in part 2, the ammeter reads 0 because the circuit is not connected. A voltmeter does not create a connection between the two wires, and the voltmeter reads 3 volts as the voltage difference at I2 is 3 volts. For question 5 on the experiment, the table shown at 5 shows the potential difference between positions on the left side and then the potential division in volts on the right side. For 6, the current is 0.02 everywhere. For 7, the sum of the potential difference over the circuit is 0, which goes back to our loop rule. For 8, there's a sketch of the potential difference versus position on the circuit, and that sketch is shown below. For 9, the ammeter doesn't change because of the loop rule, current in equals current out. For 10, the ammeter reading is 0.02 amps. For 11, the ammeter now reads 0.06 amps. This is because the current takes the path of least resistance, which is now through the ammeter and not through the resistor, when the ammeter is connected to the circuit in parallel with one of the resistors. This causes the current to be higher and the resistance to be lower, as current and resistance are inversely proportional. For 12, the resistance of the 47 ohm resistor is a resistance of 47 ohms. Resistance of a 100 ohm resistor is resistance of 100 ohms. Resistance in the wire is 0 ohms, and resistance to the ammeter is 0 ohms. In real life, the resistance of the wire and ammeter would not be 0. For section 3 of the experiment, light turns on and then immediately dims until it's no longer producing light. The current in the circuit is stopped by the capacitor, and charge was building up in the capacitor. As the charge is decreasing over time with the capacitor, the current is also decreasing in the circuit, and we found that the charge of the capacitor is equal to the discharge of the capacitor throughout the circuit. The plot measurements discussed here and shown here were also discussed in the beginning of the slide. Sources of error in this lab, the only source of error was in section 3 where I took a screen recording, which was not super accurate, which could lead to why my number was slightly off with the R times C prediction. what if questions. The first one, the real ammeter would have a slight resistance and not an ideal resistance of 0. Change the circuit by lowering the current. And for question 2, an ideal model would predict that the capacitor would reach full charge instantly. In real life, this wouldn't happen because a real wire has some resistance and would not cause a non-instant charge of the capacitor.